All right, so we're on page 4 of the chapter handout where it says electronegativity. Electronegativity is the ability of an atom to attract electrons to itself. You learned about this in biology. Electronegativity increases up and to the right on the periodic table. The electronegativity values are given in this figure on the chapter handout. Okay, so this is what we'll be referencing when we determine the type of bond that we have: nonpolar or pure covalent, polar bond, or ionic. Okay, you do not memorize these values. They will be given to you on the test if needed. Okay, so let's say I have an oxygen-hydrogen bond, which is the example in the middle of the chapter handout. So when you have an oxygen-hydrogen bond, it looks something like this. Okay, oxygen has an electronegativity value of 3.5. Hydrogen has a value of 2.1. You subtract the numbers so you get a positive difference. So 3.5 minus 2.1 is 1.4. Okay, and the ranges for determining the type of bond that you have are as follows. 0.0 to 0.4 means a nonpolar bond. This type of a bond is also known as a pure covalent bond. When you have a bond that has an electronegativity difference that is greater than 0.4, you're going to have a polar bond. That means that the electrons are not being shared equally between the two atoms in the bond. And the third difference is greater than 2.0. This is an ionic bond. Ionic bonds typically occur when you have a metal and a nonmetal. Okay, so nonpolar bonds are sharing electrons equally. Polar bonds are not. So in this oxygen-hydrogen bond, I have a difference of 1.4, which puts me at the polar bond range. So this is a polar bond, which means that electrons are not being shared equally. Electrons are drawn to the more electronegative element, which would be oxygen. There are two ways to denote that. You can have a partial negative symbol on the oxygen, because that's where the electrons are hanging out, because it's more electronegative, and then a partial positive on the other end. You can also have an arrow pointing in the direction of the more electronegative element. So you would have an arrow pointing in the direction of the oxygen. You put a little plus sign on the other side, which is where the partial positive end is. Okay? Okay. If you take a look at student exercise number 9, I've given you 3 examples. So the first one is strontium and fluorine. Strontium has an electronegativity value of 1.0. Fluorine is 4.0. You subtract those two values so you get a positive difference. 4 minus 1 is 3. So my electronegativity difference here is 3, and that falls within the ionic bond range. So I have an ionic bond between strontium and fluorine. The next one is N and Cl. Nitrogen is 3.0, chlorine is also 3.0. If I subtract those two, I get a difference of 0. So that means I have a nonpolar bond, also known as a pure covalent bond, which means electrons are being shared equally. The third example is nitrogen and oxygen. Nitrogen is 3.0, oxygen is 3.5. You subtract those two, you're going to get a difference of 0.5, which means this is a polar bond. Electrons are not being shared equally. Since oxygen is more electronegative than nitrogen, it is drawing electrons to itself. Okay? Okay, now this is the very first step in determining whether or not I have a polar molecule. So now that you know how to determine if we have a polar bond, we're going to go on to student exercise number 10, and that's carbon dioxide. Okay, so carbon dioxide looks like this, right? This is on the top of page 5. I've got one type of bond, right? I have a carbon-oxygen bond on either side. So really, you only have to determine whether that bond is polar once. Okay, so I've got an electronegativity value of 2.5 for carbon and 3.5 for oxygen. So I subtract that value once, because that's the only type of bond I have in this molecule. So 3.5 minus 2.5 is a difference of 1.0, and that is a polar bond. Okay, so the carbon-oxygen bond is polar. Now you need to ask yourself, what is the molecular geometry? My molecular geometry is linear because this is an MX2 designation. Okay? When your molecular geometry is linear, trigonal planar, or tetrahedral, you can see it on the board right behind me, there's a flow chart. Okay? When it is a symmetrical geometry, then you ask yourself, are the same atoms bonded to the central atom? And yes, they are. I've got oxygens bonded to carbon. If the same atoms are bonded to the central atom, the bond dipoles will cancel and you have a nonpolar molecule. So carbon dioxide is a nonpolar molecule. And you're going to want to memorize the flow chart that's on the board behind me, because that is what you follow to determine whether or not you have a polar molecule. So let's take a look at student exercise 11 as another practice problem. We have water. Okay, water looks like this. I have one type of bond, an oxygen-hydrogen bond. Oxygen is 3.5, hydrogen is 2.1. Subtract that value so you find out whether you have a polar or nonpolar bond. 1.4 is your difference. So that means I have a polar bond. And then what you want to do is figure out what the molecular geometry is. It's MX2E2 for the designation. That means you've got a bent molecular geometry. So, is the molecular geometry symmetrical? No. It would have to be linear, trigonal, planar, or tetrahedral to be symmetrical. So since it's bent, I have a polar molecule. So water is a polar molecule. Okay? I'm going to skip the examples that are at the bottom of page 5 in student exercise number 12, and we're going to go straight to the worksheet. So let's take a look at the worksheet. The worksheet is titled Molecular Polarity, and it looks like this. Okay? I walk you through all the steps for determining whether or not you have a polar or a non-polar molecule. The only funny Lewis structure that you might have on this one is C2H2. So I'm going to do C2H2 with you. C2H2 looks like this. Okay. Now, when you have a molecule that's made of mostly carbons and hydrogens, this is a typical organic molecule. When you're determining whether it's a polar molecule or not, and this is the only one that you do this with on the worksheet, that's why I'm doing it with you, you put a dashed line down the middle to see if it looks perfectly symmetrical on either side, and it does. That means it's a non-polar molecule. Okay, so this is the only exception that you can do this with on the entire worksheet. Okay? All right, that's it. You just do the rest of the worksheet and then submit it onto Canvas.